Hello friends, in this tutorial we will understand the basic concepts of data collection, machine learning terminology, AWS data stores, AWS migration tools, AWS helper tools that are much needed for data collection.
Now this chapter is going to cover everything you need to know about the data collection, but before we go any further, I want to introduce you the machine learning cycle. Now, this cycle is going to be used throughout this course, and what it represents is the iterative process of machine learning. Now, we start by fetching our data from different sources. Once we have our data, it needs to be cleaned and prepared before we send it to our model. Now, after we send it to our model, we need to evaluate our model to see if our model's actually any good. After that, we want to see our model is in action. So, we will talk about deploying our model to production and how to monitor and evaluate our model. After our model is in production, we can use the results to feed back into our model, and so the iterative process continues. We will recall this diagram throughout the course, and I will talk you through each step along the way. So for the first two chapters, we will talk about fetching our data and different ways to collect data and get into AWS. Now, the goal of this chapter is to actually understand what problem you are trying to solve. Once we have a good understanding, we need to understand the different parts of our input data, and then finally, we need to be able to map our data into AWS. This chapter is going to cover different topics in all these areas. So when you are ready, let's go ahead and get started. So we will talk about data collection concepts. So we are going to take the machine learning process one step at a time. Now don't worry if you don't understand many of these terms, as we will go through each of them throughout. But before we go any further, I would like to go into a brief history of the term machine learning. In the late 1950s, a guy by the name of Arthur Samuel published a paper in the IBM journal titled The Studies of Machine Learning Using the Game of Checkers, and what he coined was the phrase machine learning. Now, in this paper and through his studies, he wanted to find out if a computer could be programmed so that it will learn to play a better game of checkers that can be played by the person who wrote the program. Now, this may not be the very first time that machine learning or artificial intelligence was seen in our history, but his studies led to the creation of a program that was among the world's first successful self-learning programs, and it demonstrated the fundamental concepts of machine learning. So let's go ahead and continue this chapter and start talking about how we would collect data and what our data could look like. We will talk about some terminology, and then we will dive into how to get our data into AWS and some different services that we can use to help us with this process. So in a perfect world, our data is going to look like this. It's all put together, and neatly it forms this beautiful set. Now, that's in a perfect world, but in reality, our data most of the time looks like this. It's unstructured, it's not prepared, it needs some work, it's in different formats. It's just not what our machine learning algorithm or our machine learning model needs. And sometimes our data look like this, where it's just a garbage and our machine learning algorithm or model is not going to be able to come up with any good predictions or infer any decent information from it. So finding good data or relevant data to the problem at hand can be difficult. But let's look at some different ways of comparing good data to bad data and why. Hopefully, during the data collection process, we have enough data or large enough data sets that help us generalize our problem at hand. We need to have enough data points that describes our data so our machine learning algorithm can infer some important information about that data. So, traits of good data would be large data sets, and this is because more data usually means better model training. Next, within that data, we hope that we have precise attribute types that are feature rich. That means the attributes within our data points are actually relevant to the problem at hand. Next, within that data, we hope that we have precise attribute types that are feature rich. This means that the attributes within our data points are actually relevant to the problem at hand. Next, we hope that our data sets are complete with no missing values. If we have gaps within our data set, our machine learning algorithm may not be able to handle our data set. Next, we hope that our data points or values are consistent throughout, and this is because models like clean and consistent data. Next, we hope that we have a solid distribution of outcomes and our data is not heavy loaded with many positive outcomes and only a few negative outcomes, or a few positive outcomes and a lot of negative outcomes. Our model is not going to be able to learn much from skewed outcomes. And finally, we want to find data that has a fair sampling or data that is collected in a general sense. And this is because models will skew results with biased data. Now, you might be asking the question, well, how much data do I actually need? Well, it really just depends on the problem that you are trying to solve. But generally, you should have at least 10 times as many data points as the total number of features. Now, this is just a general rule of thumb, and we could always add more data or take a smaller sample of our data. So, where does data come from? Well, data can come from many different places, and it can be in many different formats. We can have static data and we can have streaming data. And no matter how we actually get our data, we are trying to build a data repository, and we must find a way to congregate all of our data into a single repository. And once we have it within a single repository, we are able to analyze it and use it within our machine learning process. I wanted to emphasize the importance of data and data collection and what makes up our data, because as we will find out later, collecting data and cleaning data and preparing our data is the most time consuming part of our machine learning processes. We have to have the right data that is in the right format before we are able to use it for anything useful in machine learning. So that's it for this lecture. If you have any questions, then please post your questions in the comment section and I'll try to answer it. In this lecture, we will talk about general data terminology. Now, the reason that I wanted to go through this lecture and next lecture is because there are a lot of terms used in machine learning and data science that can be used interchangeably and will use throughout this course. And I wanted to make sure that you, me, and everyone else that takes this course is all on the same page. When we describe an element of our data or we describe a machine learning term, we all know what it means. Now, as I was mentioning earlier, data is an integral part of machine learning, and we must understand the terminology that allows us to define and describe our data. So, we are all on the same page and we can all speak the same language. Now, many of these terms you are probably already familiar with, but I just wanted to quickly run through them. So, we are all on the same page. Now, the first term that I want to discuss is a data set. And this is the data that we use in machine learning. Now, datasets can come in many different forms, and we will take a look at some different types of dataset here in just a little while. And as far as terminology, a dataset is the same thing as input data and the same thing as training or testing data. We'll use these terms interchangeably throughout this course and throughout the machine learning process. Now, an example dataset might look like something like this. Now, we have some important parts of our dataset that actually describe our data, and some of the parts that describe it are columns and attributes. And we can see here we have a couple of different columns and attributes. We have name and evil, and we will use column and attribute and feature interchangeably to describe our data. And we also have a row or an observation. These are the different data points that make up our dataset. So we'll use row and observation and sample and data point all interchangeably. Now, not only do datasets come in a table format like we described earlier, but they can also be in other formats like comma separated or in JSON. And not only can our data sets that we use be described in a table format or comma separated or JSON, but they can also be described as images or video or audio. Now, depending on the problem that we are trying to solve, our datasets can come in many different forms and many different shapes and have many different mediums. Now, the way that we organize our data can be defined in a few different ways, and we can have structured data which has a defined schema, and all that a schema is just information about the data. So, for example, attribute names and data types that describe those attributes. Just think about SQL databases, relational databases, or data that's stored in table and row format. Now, structured data is the pinnacle of what we want our data to look like, but a lot of times our data is organized as unstructured data, and unstructured data has no defined schema or really any structural properties. This makes up the majority of our data collected. So you can think about things like PDFs or images, video, audio, and pretty much all the other data collected throughout. We can also have data that is in the middle, that's semi-structured, and this data is too unstructured for relational data, but it has some organizational structure. You can think about this data as a NoSQL data or non-relational data. Most public datasets data that's in CSV, JSON, or XML format. So for a quick visual of structured data versus unstructured data, you can think about structured data as being neatly defined and well organized. And you can think about unstructured data as data with less organization or no organization, with no defined schema, and the data types are not described. So for structured data, we can think about these as our traditional relational databases. You can see by the ERD diagram, and some good example of unstructured data would be things like audio files, maybe log files, and things like tweets or social media streams. Now, we talked about structured data and how relational data fits in structured data. So where is relational data stored? Well, in things like databases, and databases can be defined as a single repository for applications or other services that are transactional, meaning that whenever we write to a transactional database, if the operation is not successful or some error occurs, the changes are rolled back. And you could think about databases as your relational traditional databases that are made up of two tables with rows and columns. Now, the next type of data repository or the next type of data store that I want to discuss is a data warehouse. And unlike a traditional database, data warehouses collect data from many different sources in many different formats and congregate them all together into a data warehouse. And traditionally, before the data lands into the data warehouse, there is usually some type of processing or cleaning of that data that happens before it lands within the data warehouse. And this is because the reason we want our information in a data warehouse is so we are able to run analytics, use BI tools, and find out important information about our data. Data warehouses are used to store petabytes and exabytes of data and gives us the ability to analyze it more easily. And the last type of data repository we'll talk about are data lakes. And traditionally, data lakes store massive amounts of unstructured data that are dumped into a single repository or a data lake. And traditionally, there is really no processing done before we dump the data into a data lake. You can think of it as a one-stop shop for dumping our data. A lot of times we use data lakes to store historical data or data we are not really sure what to do with yet, but we know that's important and we need to store the information off. So the main thing to remember between a data warehouse and a data lake is there is usually some processing done on data before we insert it into a data warehouse. Unlike a data lake where there is usually not any pre-processing done to the data, we just dump it off and forget about it. So for a quick summary of our data repositories, databases are your traditional relational databases like MySQL and SQL Server. They are transactional and there is a strict schema that defines our data. And remember, with a data warehouse, the processing is done on import and the data is usually classified or pre-processed with the user in mind, meaning that whenever we add the data to the data warehouse with business intelligence tools and we are able to query and analyze our data. And finally, we talked about the data lakes where the analysis or the processing of that data is done on export. Data lakes are used to store many different sources and many different formats. And usually the data is in the raw format and it's really not ready to use. That's why we must process it on export. So that's it for this lecture. I hope we are all on the same page with what datasets are, what structured and unstructured and semi-structured data is, and hopefully we have a good understanding of different types of data repositories or different type of data stores that we can use to store our data. If you have any questions, then please post it in the comment box. I'll try to answer it. Let's move to next chapter. We'll talk about some machine learning data terminology that is not too difficult to understand, but throughout the course, there is a lot of terminology. To start off, we have talked about different type of structured and unstructured data. But in terms of data that we use within our machine learning models, it can usually be defined as labeled data or unlabeled data. Now, labeled data is data where we already know what the target attribute is or data that has the correctly predicted value assigned to it. And as you can imagine, unlabeled data is data that is collected with no target attribute. So let's take a look of an example of some labeled data. So for example, we have some emails and we are trying to determine whether these emails are spam or not spam. Now, we read all the content of the email and we find out that 2 of the 6 are spam emails, and we can translate these findings into a data set that looks like something like this. We have information about the data set. For instance, the form domain, the body, what is actually contained within the email, some other attributes, and then whether it's a spam or not spam. Now, in our case, this data is labeled because we know whether it's a spam or not spam. So in this case, the spam would be the label or the target attribute, and we are able to determine whether it's a spam or not spam by the variable or the features associated with that email. So things like where did the email come from? What did the email say? Is it possible that the email contained things like send money or click here now? Another example of labeled data would be things like image data, where it has a tag associated with it. So for instance, we have some different images of planet in our case. The name would be the label for this dataset. Now, some examples of unlabeled data might be things like audio stream or log files or Twitter streams or social media streams. The reason that this is unlabeled data is because it's really just general data collected. There is really no answer or tag associated with it. Now, for some more examples of unlabeled data and labeled data, think about the labeled data as spam or not spam emails like we saw earlier. Think about labeled handwritten digits, data about housing prices, tagged images of tumors that are benign or malignant, things like customer churn data. Did the customer come back or did the customer unsubscribe? Looking at data about fraudulent or non fraudulent credit card transactions, and also looking at the labeled audio and video data. For instance, is the video stream of a person or is this audio file of a dog barking? If the video or audio stream has a tag associated with it, then that would be labeled data. Now, some examples of unlabeled data would be things like just general customer information, things like new articles, general surveillance, video captured, things like log files on a server. We saw that general tweets or social media streams can be unlabeled data. Things like blog posts and things like web traffic accesses, as in who accessed the website and what did they click on, and things like stock market prices. All of this unlabeled data is just general data collected without a target, attribute associated with it, or a label associated with it. Now, we'll talk about supervised and unsupervised learning in a later chapter, but just know that majority of the time supervised learning is done with labeled data and unsupervised learning is done with unlabeled data. And as mentioned earlier, we will dive deeper into this in the later chapter, but for now, just keep this in mind. Now, the next terminology that I want to discuss describes some of the features within our data. Now, we can have features within our data that can be described as categorical data. Categorical features are values that are associated with a group. So, these values are qualitative and they are discrete, meaning they can only fit into a finite group of values. And continuous data or continuous features are values that are expressed as a measurable number. And these values are quantitative. And in theory, continuous data is infinite, meaning it can grow as large or as small depending on how it's defined. So, a couple of terms that I have gotten confused are the ideas of qualitative data and quantitative data. Now, the way that I remember these are qualitative data has an L for categorical and quantitative data has an N for continuous. Or you could think about it's a numeric value. So, this is just a quick tip that I like to think about when trying to determine the differences between the two. Now, an example of categorical data or a categorical feature with our data can be described in this dataset, which is a dataset that just describes the height and weight of a dog with some other attributes and the group or the categorical variable associated with this dataset is the breed of dog. And as you can see, there is only a discrete number of breeds or dog types that these observations can fall into. So you can imagine the breed as being a categorical variable. And we also saw a categorical feature in a previous example. When we decided whether an email was spam or not, the spam feature can be described as a binary categorical variable, right? It's either true or false, yes or no, 0 or 1. And just remember that if the attribute falls into a group or a category, then the attribute is categorical. Now that we have looked at categorical features, let's go ahead and take a look at some continuous feature examples. So here we have some information about houses like the number of bedrooms, how big the home is, by the square feet, some other attributes, and then the price of the home or how much the home costs. Now, in this case, the price is a continuous feature, right? It's a quantitative value that can fit on a number line. The prices of these homes don't fit into a specific group, and you can think about these prices going to the dollar, to the penny, to the tenth of a penny, to the hundredth of a penny, etc. And remember, if we can fit the value on a number line, then these are going to be continuous features. As we continue down our machine learning journey and start collecting data, we will find that some data is unlabeled and labeled. We will find that some data is categorical and continuous, and all of this really just depends on the type of problem that we are trying to solve. And this goes back to what type of data that we need to collect. Now, our data might consist of some of these or all of these. It really just depends on the problem at hand and what type of data we need to collect. Now, the next few terminologies I want to discuss have to do with some different type of data. Now, in machine learning, we can have data sets that consist of text data or also known as corpus data. These are data sets that are collected just from the text. You will see this type of data used in different natural language processing applications. Things like speech recognition, text to speech, and more. And this text data can be words, phrases, spoken languages, fiction literature, things like magazines and newspapers, and academic sources, and dialogue between two people. Now, some examples of text data might look like this, where we have an academic paper, we have a dialogue between two people, and we have a newspaper clipping. And text data can also look like this, where we are possibly trying to predict a third word. And so we have different combinations of first word, second word, and we are looking at what the third word could be. The important thing to remember is that corpus data is the same thing as text data, and this just refers to the data set collected from the text. Now, the next terminology I want to discuss is known as the ground truth data, and this is just a general machine learning term for datasets that refers to factual data or data that really already been successively labeled, and we can trust this as a truth data. So for example, if we reviewed several video clips and we labeled them whether a person was in the video clip or not in the video clip, we could then deem those video clips as ground truth data because they have been defined with a label and we can trust it as truth data. The reason that I bring up ground truth is because there is a service within AWS called Amazon SageMaker Ground Truth, which is a tool that helps us build these ground truth data sets by allowing different type of tagging and labeling process. And essentially what this tool is, it allows us to easily create label data. Now in a later chapter, we will talk about another tool that is integrated directly with the SageMaker Ground Truth that allows us to have real humans labeled our data sets. It's called Amazon Mechanical Turk, and it gives you a really cool lesson on where the term actually comes from. And you can see Amazon SageMaker Ground Truth in the console here, and what it might look like for someone who is trying to label a dataset is they may be presented with the following screen, and within this they are asked a question, well, which sport is being played? Now you can think about having hundreds and hundreds of these images, and there is really nothing assigned or tagged or labeled with these images. So we can use SageMaker Ground Truth to tag these by assigning them to a specific label and then submitting those through the workflow and gives us the opportunity to actually label and tag our data. Now, the next type of data that I want to discuss is image data. And image data can come in many different forms and many different shapes. And essentially, image data refers to data sets with tagged images. And image data can be used for analyzing facial recognition, action recognition, things like object detection and handwritten characters. It can also help with gender classification or age prediction and much more. There are several image repositories that are out on the web that I'll post to the description section, and we will look at here just a little while that have thousands and thousands and millions of images that are already tagged for image classification. So let's take a look at some image data examples. We could have a couple of examples here, and so in this case we have the first image has been tagged as a rodent. The second image has been tagged as the handwritten letter M, and the third image has been tagged as a hot dog. Now, we will talk more about image classification problems and how we could possibly use these data sets to solve our machine learning problem. But for now, I just wanted to mention what some image data looks like and how important it is to have labels associated with our images. Now, speaking of the data sets that are out there that we can use, the first one is described as the Mnist Data, which is a collection of handwritten characters that are broken down by pixels that help us define what a handwritten characters would look like. We can use these to compare against other handwritten images to determine what letter or what number is associated with a handwritten letter or handwritten character. Now the next type of data repository that's free to use is the image net data set, which is a hierarchy of image classification. Now all of these images are tagged and we can pretty much search for any image and find tagged images to help train or to help build out machine learning problems. I'll post the link in the resource section of this chapter to show you what these data sets look like. Now, the next type of data that I want to discuss is known as time series data. And if you can imagine, time series data just refers to data sets that capture changes over time. The main example of time series data that I like to think about is stock market prices. We can capture the prices of different stocks over time. So we can consider this time series data. You can also think of time series data like sensors in a Raspberry Pi or IoT devices and things like web traffic or log files. We can use time series data to help identify things like trends and patterns within our data. So, for a quick summary, let's just discuss some different dataset examples that we might find in machine learning in general, and we talked about how we could use image data for things like facial recognition, action recognition, and object detection, handwritten and character recognition. And the format that image data comes in is usually images or video. We also have text data, and some example cases are reviews or news articles, messages, Twitter and tweets, and dialogues between two people. And the format, as you can see, would be text or CSV. Now, we did not specially discuss sound data, but you can think about things like speech or music or the sounds, and the format of these would be an MP3. And we will find out later how we can represent sound data with text. We can also have things like signal data like electrical signals or motion tracking or chemical compounds, and these can be in the format of text. We also have things like physical data like high energy physics systems astronomy, and earth sciences. And the format of these would be something like text. We can also have biological data, and this is the information about humans and animals and plants and microorganisms. And finally, most other data falls into the multivariable data, which is things like financial data, weather, census data, transit information, internet, and games. And these can be in several different formats, but we typically see them in the CSV or text. So, here are just a few examples of different types of data, what they look like, what they might consist of, and the different elements that make up our data. Now, this is the end of the lecture, but these are not the only terminology that we use in machine learning. I just wanted to go over these upfront to you so we are all on the same page and we can all speak the same language. So if you have any questions, please post it in the comment box and I'll try to answer it. Then join me in the next lecture where we will start to discuss the different places in the AWS where we can start to store our data. So when you are ready, we'll start the chapter. So far, we have covered different areas of why data collection is so important. We have also talked about some different terminology that we will use throughout this course. And finally, we are at the point where we will talk about some different AWS services that we can use to store our data for our machine learning problems. Now, the next few lectures cover different ways on how to get our data into AWS. But at the core of it all, we are really just trying to get our data into AWS S3. So, if you already have an associate level certification, you should already be familiar with this service and all the other services that we'll discuss. But we will briefly discuss what Amazon S3 is and the other services throughout this lecture. Amazon Simple Storage Service or S3 provides us a way for unlimited data storage that provides object based storage for any type of data. And this essentially is the go to place for storing our machine learning data. And the reason for this is because the core services that AWS offers for machine learning integrates directly with S3 and make it super easy to read and stream our input and testing data from S3 onto these machine learning services. It also uses S3 to output the result of anything that we create within our machine learning process. So let's continue and talk about a few other features of S3. S3 objects or files can be from 0 bytes to 5 terabytes and there is unlimited storage. And what I mean by unlimited storage is AWS monitors how much data is on S3 and if it looks like they are hitting a threshold or getting close to hitting a threshold, they will provision more resources so there is enough space to store all of your data. Now, files and objects are stored into buckets, which are similar to folders, and S3 has a universal namespace, meaning that the names of your buckets are unique globally, meaning that you cannot have the same bucket name as one of my bucket names. So this is what an example endpoint of an S3 bucket would look like. It has S3, the region, Amazon AWS.com bucket name. So in our case, the bucket name would be machine learning data. AWS supports two different ways to address endpoints with path style like I just showed you or the virtual hosted style. Recently announced, the path style model will actually end in September 2020. So from this point forward, our bucket names are going to look like this. This is the virtual hosted style and what it looks like is the bucket. So this is what the new endpoints or the virtual hosted endpoints are going to look like moving forward. So the next question is, well, how do we get the data into S3? Well, if your data is already into S3, then you are good to go. But if you need to upload data into S3, there is a few different ways you can do this. The first and most straightforward way is to just upload it through the console. You can simply click the upload button and upload your datasets or your objects manually. You can also upload datasets to S3 using many different SDKs that AWS offers to upload the files via code, or you can use the command line interface to upload your data into S3. The next type of data store that we will discuss is RDS, which is Amazon's relational database service, and this is for relational databases. And we discussed earlier how we could have structured data with a defined scheme within our relational databases. Now, RDS has the following engines that you are allowed to choose from to create a fully managed relational database. As mentioned earlier, relational databases are for application data stores that need transactional style databases. Now, in the console, we can create an RDS instance, choose our engine type, set all the parameters, and then create a relational databases right in the AWS console. The next service we will talk about is Dynamodb, which is a NoSQL database or non-relational databases that is used to store key value pairs. Now, this service is the best for schema-less data and unstructured or semi-structured data. And the example of what some data in DynamoDB might look like is the following. So here we have some data about star war characters and it's semi-structured data in JSON format. Now all of this data is considered the table in DynamoDB and the actual table name is defined as characters. Now within that table we have different items. So we have two items here, and then within those items we have key and value pairs. So a key value will be a weapon and the value for that key would be lightsaber, and the combination of a key value pair is going to make up an attribute, and within the AWS console it gives us a user interface where we are able to interact with our NoSQL database. Now the next type of data store that I would like to discuss is Amazon Redshift. So check that out if you get a chance. Now, Amazon Redshift is a fully managed clustered petabyte data warehousing solution that congregates data from other data sources like S3, DynamoDB and more, and it allows you to store mass amount of relational or non-relational semi-structured or structured data to create a data warehousing solution. And once your data is in Redshift, you can use SQL client tools or business intelligence tools or other analytics tools to query that data and find out important information about your data warehouse. And within the console, you can launch your Amazon Redshift cluster. Select the number of nodes that you want, their storage size, and other parameters to create your data warehousing solution. Another cool feature within Redshift is a tool called Redshift Spectrum, which allows you to query your Redshift cluster that has sources of S3 data. So essentially, it allows you to query your S3 data. You can then use tools like QuickSight to create charts and graphs to actually visualize that data. Now we will talk more about QuickSight in a later chapter, but for now just understand that it's a business intelligence tool. Now the next data store that I want to discuss is Amazon TimeStream, and this was actually announced at reInvent 2018. Now in the earlier lecture we talked about time series data, and this data that's from things like IoT devices, IT systems, smart, industrial machines, things like server logs or any other time series data. So think about stock market prices. Amazon TimeStream is a fully managed time series database service, and it allows you to plug in business intelligence tools and run SQLite queries on your time series data. And the last data store that we will discuss is Documentdb. Now, this was announced at the beginning of 2019, but essentially all Documentdb is a place to migrate your MongoDB data. It provides better performance and scalability than your traditional MongoDB instances that are running on something like EC2 or on premises. Now, that's the end of this lecture. Now, I understand that I touched on many of these services at a very high level. I will make a detailed video on these series in upcoming video lecture. So, which will definitely go more in depth and provide little extra layer of knowledge. So, remember, we are trying to set our data in S3, and if your data is in any of these services, then we have to use some different migration tool to import the data to S3. So, in the next lecture, we will talk about different migration tool. In the last lecture, we talked about different places that we can have our data on AWS or stored within AWS. And in this lecture, we will talk about different migration tools that we can use to help us get our data into S3. So it's ready for our machine learning process. Now, if our data is already in S3, then we are good to go. But what if it's not in S3? What if it's in another service like RDS or Dynamodb? We will talk about different migration tools that can help us move our data from one service to another. Now, remember that there is no one size fits all service to get data into S3. Every data source can vary in process and depending on many different factors and efficiency and our source and destination data types, the structure of our data and the expected output of our data. So, the different tools that I'll cover throughout this lecture will help you get a better understanding if which type of migration tool is best for your situation. If you have data in one location, what's the best tool or strategy to use to get into another location? So, the first migration tool that I'll discuss is Data Pipeline. Now, Data Pipeline allows you to process and move data between different AWS compute and storage services. And it also allows you to transfer data from on-premise data source onto AWS. What you can do is set up input from different data sources like DynamoDB, RDS, and Redshift. Set up a data pipeline and then output that data onto S3. Now, Data Pipeline offers several built-in activity objects that allows us to copy data using a few different activity types. Things like SQL activity, which allows us to specify SQL queries, and things like Redshift copy and shell command activity. We can use these different activities and specify which type of data source that we have and how we want to migrate our data. We can set up these pipelines to run on some schedule or to run on demand. Now, data pipeline can also be used as a transformation tool, but in this context, we are just talking about moving data from one location to another. And within data pipeline, you are able to manage the pipeline execution, the resources that actually transfer the data. So think EC2 instances and any retry logic and failure notification if some type of transfer is not successful. Now, within the AWS console, they have several built-in templates that you can use when creating your pipeline. And you can do things like move data to and from Dynamo to S3, RDS to S3, Redshift to S3, etc. etc. You can also provide your own templates for custom pipelines that you build yourself. Now, the next tool that we will discuss as a migration tool is DMS or Database Migration Service. And this service allows you to migrate data between different database platforms. Now, this tool is generally used for transferring data between two different relational databases, but you can also output the result onto S3. Now, DMS support homogeneous and heterogeneous migration, meaning if you wanted to transfer data from MySQL to MySQL, this would be considered homogeneous, and you are also able to transfer data from things like, let's say, SQL Server to S3 or SQL Server to MySQL. This would be considered a heterogeneous migration. So think about the different databases service like on-premise databases, databases on EC2, or databases on RDS. We can use the DMS service to transfer our data onto S3. Now, DMS doesn't support really any transformation other than possibly a column name change or something along those lines. But traditionally, you wouldn't use this as a transformation tool. What you can do is set up a source and point for any of these types of sources and have the data output on any of the target endpoints. And as mentioned earlier, it supports heterogeneous and homogeneous migration. So DMS is a pretty great tool for relational databases, but it also allows you to output your data onto S3 if needed. Now, the main difference between data pipeline that we just discussed and DMS is that DMS handles all the heavy lifting for you. When it comes to resources that are required to transfer the data, data pipeline allows you to set up your resources as needed and handles the transferring of data in more of a custom way. And last but not the least, we will talk about using AWS Glue as a migration service. Now, AWS Glue is a fully managed ETL service which stands for extract, transform, and load. But we are mainly going to focus on the loading portion since we are talking about the migrating data. Now, we are going to go much more into depth on AWS Glue in a later chapter. So, we'll touch it at high level here and we'll talk about how we can load data into S3. Now, the parts that make it possible to migrate data onto S3 is that when we use AWS Glue, it creates table within a data catalog that are kind of like a skeleton for our dataset. It's essentially the metadata and data types and attribute types that make up our datasets. Now, to create these tables within AWS Glue, we set up a crawler that essentially goes out, looks at the data, and it determines the schema associated with that data. Now, within these crawlers, there are several different classifiers that work at hierarchy level and go down the line to try to infer what type of data it is or what type of schema it is. So, even if you have some unstructured data or possibly schema-less data, the built-in classifiers that AWS Glue offers help us build a skeleton of some type of schema associated with our data. Now, if a classifier can't recognize the data or it's not 100% certain, the crawler invokes the next classifier and determines whether it can recognize the data. You can think about these classifiers as being similar to a regular expression that can kind of go along and try to find some type of schema or some type of structure in your data. You can also create custom classifiers that specially lay out what your data looks like. So, what we can do with AWS Glue is take data from any of these input data sources and set up a crawler and classifiers to try to define the schema if possible, and then output the data into other AWS services like Athena, EMR, S3, and Redshift. Now, don't worry, we will cover Athena and EMR in the next lecture. But for now, just know that we can use AWS Glue to load our data from one data source to another. And during the loading process, we can change the output format to any of these formats to get it ready for our machine learning model. So let's take a few scenarios where we have data in one location and we are trying to get it into S3. Let's see if we can choose the right approach. Now, in our first scenario, we have some data that's in a PostgreSQL RDS instance and we need to get that training data onto S3. Well, we can use AWS Data Pipeline as our migration tool and specify a SQL activity query that places the output data into S3. So, let's say we have some unstructured log files in S3. Well, what we can use is AWS Glue to create custom classifiers if the built-in classifiers can't recognize a schema, and output the result into S3, for instance, in CSV format. Now, for the next example, let's say we have some clustered Redshift data. Well, we have a couple of different options. We can use AWS Data Pipeline as our migration tool and specify a SQL activity query that places the output data into S3. So let's say we have some unstructured log files in S3. Well, what we can use is AWS Glue to create custom classifiers if the built-in classifiers cannot recognize a schema and output the result into S3, for instance, in CSV format. Now, for the next example, let's say we have some clustered Redshift data. Well, we have a couple of different options. We can use AWS Data Pipeline and the unload command to return the result of a query to a CSV file in S3. Or we can use AWS Glue to create a data catalog describing the data and load it into S3. And finally, the scenario of having an on-premise MySQL instance with training data that we need to get into S3, well, we can use the AWS Data Migration Service to load the data in CSV format onto S3. As mentioned earlier, there is no one size fits for all. Choosing a migration tool to get your data from one AWS service to another. Each tool has their pros and cons, and it really just depends on how fast you want your data to be migrated, and if it cost is a factor, and whether or not you need some type of transformation done to your data. Now we will talk about data preparation and transformation in a later chapter, where we will discuss different tools that we can use to help us transform our data. But for now, these are just some different migration tools that help us get data from one service to another. Now, as mentioned earlier, you may get questions that ask you how to migrate data from one service to another. And so I hope these tools give you a better understanding of what type of migration that you can do. So if you have any questions, then please post it on the comment section and I'll try to answer it. Then let's move on to the next lecture. We have looked at different data stores where we can store our data within AWS, and we have talked about a few different migration tools. Now, I want to cover some helper tools that can help us get our data into AWS and also help us store our data within AWS. Now, these tools did not fit directly within the last two lectures, so I wanted to briefly discuss them here. And we'll start by talking about EMR. Now, EMR is a fully managed Hadoop cluster ecosystem that runs on multiple EC2 instances. And what EMR allows you to do is pick and choose different frameworks that you want to include within the cluster. This allows you to run distributed workloads over many EC2 instances. If you have petabytes and petabytes worth of data, now most of these products are open source and EMR allows you to assemble all of them together to do different things. Now, in our case, we would use EMR to store mass amount of files in a distributed file system to use as our input or training data. Now, if our data is already within an EMR cluster, we can use some of the frameworks and services to migrate the data into S3, or we can use services like AWS Data Pipeline to load the data into S3. Now, we'll talk about the EMR ecosystem at the later chapter when we start talking about our data preparation process. But I just wanted to mention it here and how it's used to store petabytes of data among a distributed file system. And you can see here from the AWS console, when we create a cluster, we can choose advanced option and select the different frameworks that we would like to use. And The last tool that I want to discuss is Amazon Athena. And what Amazon Athena is, it's a serverless platform that allows you to run SQL queries on your S3 data. Now, earlier we mentioned how Redshift Spectrum does a similar task, but we will define the difference of two here in just a little while. We can essentially set up a table within our data catalog within AWS Glue and use Athena to query our S3 data. So within the console, we can select tables that are defined within our AWS Glue data catalog. We can write a query and then output the result onto S3 or output the results onto a CSV file. So I wanted to mention Athena here so we know that we can use it to query our S3 data. So what's the difference between Redshift Spectrum and Athena? Well, they both allow you to query S3 data, but with Redshift Spectrum, you must have a Redshift cluster spun up. Now, that's not needed with Athena as long as you have a table defined within your AWS Glue data catalog. And Redshift Spectrum is mainly used by existing Redshift customers and new customers that quickly want to query their S3 data. They can use Athena for that. So, in a summary, for this chapter, after we discussed several AWS data stores, some different migration tools, and some helper tools, we are now ready to get our data onto S3 and then we can finally start using SageMaker. Now, we will cover SageMaker more in depth after a few chapters, but just know that this is our one-stop shop for machine learning within AWS. So that's it for this lecture. So you have an understanding of what these tools are at high level and how they could possibly be used during the data collection process. If you have any questions, please write it onto comment section and I'll try to answer it. Let's move on to the next lecture. So, we will quickly go over some data collection tips that I think are important for your knowledge. Now, at the beginning of the chapter, we talked about some steps and questions that we need to ask before we begin our machine learning process. We need to understand that before we gather our input data, we need to formulate a problem that we are actually trying to solve. We need to know how we can actually measure success and what are our actual goals. We also need to determine if machine learning is even necessary. Can we just apply some if then logic or a simple heuristic view? What need to understand the type of data that is available to help us solve our problem, whether it's open source or a public data set or if it's a data in-house. We also talked about what good data is and what makes up good data. And we need to understand why having good data is important. And also remember the difference between what good and bad data looks like. Next, we talked about some general data terminology and some machine learning data terminology, where we identified things like columns and attributes within datasets and rows and observations. We need to be able to understand these terms and speak the same language. You need to know the difference between structured, semi-structured and unstructured data, and you need to know the different types of data stores or data repositories like databases and data warehouses and data lakes. Remember that databases are your traditional relational transactional databases. Data warehouse are used to store mass amount of data where there is usually some pre-processing done on the data, and data lakes are used to dump off data where there is really no pre-processing done, and if we want to process the data, it's on export. We need to understand the difference between labeled data and unlabeled data, and we need to be able to reorganize categorical features and continuous features within our datasets. Remember that categorical features are qualitative and continuous features are quantitative, and we need to be able to recognize and know terms like corpus and ground truth And remember the difference between the general machine learning ground truth data set and the service that's built into Amazon SageMaker. We also need to know what time series data looks like and what it's used for, and the same thing with image data. And finally, we talked about some AWS data stores that allows us to store data within AWS. We need to know the different services and what type of data each of these services are used for. We also talked about AWS migration tools that allows us to migrate data from one AWS service to another. And remember, our end goal is to get our data onto S3, so we are able to use it within the machine learning platforms built into AWS. And finally, we talked about some AWS helper tools that allows us to store mass amount of distributed data using the EMR service and how we can use it as a migration tool by the built-in frameworks that are supplied within EMR or by using the other services like AWS Data Pipeline. We also need to know what Amazon Athena is, how it can query S3 data, and how it differs from Redshift Spectrum, and know what the use case is to use one over the other. So, congratulations again, and if you have any questions, you can post it in the comment section and I'll try to answer it.
So that was pretty much about the data collection theory in AWS. In the next video, we will talk about streaming data collection using Kinesis in AWS with practical. If you like the video, then please do visit my channel and subscribe it. Thank you.